Hello, everyone. It is my honor to present my paper named Pre-training graph neural networks on moleculars by using subgraph-conditioned graph information bottleneck. And my name is Thuy Hoang. I'm from the Catholic University of Korea. And we can see that graphs are everywhere. It's a general language for modeling the complex systems. We can see that graphs from the transportation system, social media, chemical network, and as well as program. And in here, uh, moleculars can be represented as graphs, and the nodes and the edges represent the atoms and the bonds of moleculars. And molecular graphs provides direct access to the graph or the molecular objects like atoms and functional groups. And for learning molecular structures through graph neural networks, and given the moleculars, the output is that a score for specific task predictions with the graph neural networks. And in here, we to build the pre-training strategies for learning moleculars. And uh, we present the two weaknesses of the current pre-training graph neural networks on moleculars. The first weakness is that the current methods lack the ability to generate well-distinguished graph level representations. For example, subgraph level strategies mostly based on the predefined patterns like frequent subgraphs, and they ignore global interactions between the important nodes that that provide the molecular and entire structures. And moreover, for constructive learning methods, applying augmentation schemes like edge perturbation could potentially disrupt the structures and properties of moleculars. And the second weakness is that it is challenging to cover all the possible uh, functional groups across molecular datasets. For subgraph level strategies, uh, generate the dictionaries based on the predefined rules, like counting the occurrences of subgraphs across moleculars to decompose the moleculars into a bag of the subgraphs. Commonly subgraphs with larger size and frequent occurrences. And there are the limitations like the static dictionaries could limit the model ability to capture the new and uncommon functional groups. And in this paper, we overcome the two weaknesses of pre-training strategies by considering how to generate well-distinguished graph-level representations and how to automatically capture the significant subgraphs without using the prior knowledge. And in this work, we propose a subgraph-conditioned graph information bottleneck named SCGIB for self-supervised pre-training to compress an input graph into a graph called conditioned on specific significant subgraphs without using label informations. And the fundamental idea behind our strategy is that across the chemical domains, moleculars share universal core subgraphs that can combine with specific significant subgraphs to robust representations of moleculars. So this is the overall architecture of our models. And given an input graph Z, our model jointly learns the graph core and the significant subgraphs under the SCGIB principles. So first, we inject the noise informations into the edge. Is just the output of the ZNNs to obtain the graph core Z under the compression process. And at the same time, we capture the significance specific subgraphs from the ego network routed at each node through the attention-based interactions. And in here, we propose the conditional graph information bottleneck principles. It is a modification of graph information bottleneck. So given an input graph G and a set of functional group candidates S, we define the S these CGIP principles conditioned on the subgraph S as a objective term like this. And by conditioning on S, the first term uh, encourages encourage the graph call to capture the sufficient information for reconstructing the input graph G. So we call it as conditional reconstructions. And meanwhile, at the same time, the graph call also needs to be compressed from the input graph as a compression process. For more information about the proofs, we refer readers to read our papers. And we also provide the constructive learning notes. And in here, we would say that the graph call can be too distinguished from the its input graph Z compared to other graphs, remaining graphs. And we argue that the ideal call should at least satisfy the high module information with its input graphs compared to others during the compression process. And in here, we utilize the constructive learning to maximize the agreements between the graph call and its input graphs compared to other graphs. For the experimental results, in here we provide the performance analysis on the graph classification and regression tasks. And in here we observe, we can see that our model consistently outperformed other baselines and obtaining the best performance in 10 out of 11 downstream datasets. And we attribute the superior performance of our models to its ability to generate well-distinguished representations and effectively capture significant subgraphs, substructures like functional groups. And we also provide the efficiencies analysis of different strategies. And in here, we note that the solid lines are training curves and the dashed lines are validation curves. And in here, we can see that SGGIB is considered as a one-time effort. We can significantly reduce the training and validation times on specific downstream datasets on 6 datasets. And moreover, SGIB typically exhibits stable training and validation curves. Furthermore, we also conduct the experiments on the interpretability analysis. And in here, we employed SGGIB to explain the molecular predictions compared to ground truth explanations on 4 datasets. And in here, SGGIB achieved the highest fidelity scores on almost datasets in terms of 2 metrics, fidelity plus and fidelity minus. And this implies that SGIB generates a reliable explanation that is aligned with the model predictions. And furthermore, we also conduct the visualizations of model interpretabilities in functional group detection tasks. And in here we conducted the qualitative validation on graph interpretations through visualizations on 2 datasets. And in here we can see that SCGIB can more interpret the input molecules than binary. Um, Lastly, we also conduct the experiments an ablation study on graph core and attention coefficients. And we observe that uh, this indicates that exploring graph core and significant subgraphs is important to fully generating pre-trained models as well as the property prediction in downstream datasets. And furthermore, while considering the graph core is important, exploring discovering the significant subgraphs is more beneficial for molecular property predictions. So in conclusions, we present a novel pre-training strategies for moleculars named SCGIB, which can discover graph core and significant subgraphs to generate well-distinguished representations. And the main idea is to explore the graph cores of moleculars that contain compressed and sufficient information regarding the reconstruction task conditioned on significant subgraphs under the set SCGIB principles. By doing so, SCGIB can generate diverse representations, improving the performance in molecular property prediction tasks. And moreover, SCGIB also delivers model interpretability in terms of functional group detection tasks, despite being learned from self-supervised learning. Yes, thank you for listening.